Hello everyone. In this lecture, we will derive wave equation. Let us consider a stress string of length L with ends fastened on the x-axis at x equal to 0 and x equal to L. And suppose the string is set to vibrate by displacing it from equilibrium position and then releasing it. And assuming that the string vibrates only in the fixed plane, we let uxt denote the transverse displacement at time t equal to greater than equal to 0 of the point of the string at position x. Now let us understand with the help of this diagram. Clear? And suppose this is the string, stressed string. One end is fixed at x equal to 0. Another end is fixed at x equal to L. Clear? Now if you stretch this string along the vertical direction, vertical axis, clear? So this string will look like this, clear? So this distance, and suppose this distance is x, so this distance is denoted by uxt, means u is a function of distance x and t time t, clear? And we have assumed that this string can vibrate only in the vertical direction, not along the horizontal direction, but only in the vertical direction. Clear? So I hope that now you understand it. Now move forward. We make the following assumptions. Number one, the string has a constant mass density. It means this is a homogeneous string. Every point this density is same. Clear? The string is perfectly elastic and offers no resistance to bending. Means whenever you are just bending, stretching it, so no resistance is there. The motion of the string is transverse only. It means in vertical direction only. This implies that the horizontal component of the tension is same at all points. Clear? Means no motion is there along the horizontal direction. It means this component of the tension along the horizontal axis, this will remain same because no motion is there in horizontal direction. The transverse vibration of the string are small and take place in a plane containing the x-axis and xu plane. And xu plane is this one. This plane is xu plane. Vertical plane is xu plane. Clear? Also, the slope at any point of the string del u by del x is small. So these are some assumptions for deriving wave equations. Clear? Let us consider the situation in which no external force is acting on the string. The weight of the string is negligible compared to its tension. It means the only significant force acting on the string is its tension. Let T denote the magnitude of the tension in the equilibrium position, means when no stretching is there. This tension is the same at every point of the string. For every point, this will remain same. Now consider a small portion of the string between 2 points A and B. And suppose if you look at this figure, you can assume that 2 points A and B are here. Suppose this point is A and this point is B. So this small portion is shown here in this figure, this A and B. And suppose the distances of A and B are x and x plus delta x, and suppose T1 and T2 be the tensions at these 2 points A and B. Actually, the magnitude of these two tensions are same as T, but directions of these two tensions are different. Clear? So because we don't have any motion in horizontal direction, so we need to consider only the vertical component of the tension. So if you apply the Newton's second law and first calculate the vertical component of tension, so this will be T2 sine beta, because this is in upward direction, we are taking upward direction. So look at this is in this direction minus T1 sine alpha. Clear? This is alpha, this is T2 minus. Why we are taking minus? Because if you take this in as a positive direction, so you will consider in this direction as negative direction. Clear? So apply the second rule, F equal to ma. So this is the force, combination of these two, sum of these two equal to ma, where m is the mass of that particular portion. Now look at this. We have to solve this equation. So to solve this equation, we can replace sine alpha by tan alpha. Why? How we can do it? For small angles, we can write sine alpha equal to tan alpha. Why? Because tan alpha is equal to sine alpha upon cos alpha. And suppose if alpha equal to 0, then cos alpha equal to 1. It means whenever alpha is very small, cos alpha is going to be 1. That's why for small values of alpha, we can assume sine alpha equal to tan alpha. So this equation becomes minus t tan alpha plus t tan beta m del square u by del t square. This is acceleration. And further you have written the value of m here, rho and delta x. Rho is the density. Now if you assume t is fixed and consider uxt as a function of x, so you can write tan alpha equal to del by del x of uxt. Similarly tan beta del by del x of ux plus delta x t. So this equation, put t here and delta x here in the left hand side, so you will get this equation. Clear? Now if you apply the limit delta x tends to 0, then this becomes, look at this, this becomes the derivative of del u by del x. Derivative of del u by del x, it means the second derivative of u with respect to x, because this derivative already. So if you write limit delta x tends to 0 for this expression, this will give you the second order derivative. So say this constant rho by t is c1 square. So finally you will have the equation del square u by del x square equal to c1 square del square u by del t square, where c1 square is this constant, and this is known as the wave equation. Clear? So if some external forces are there, then this equation will become like this, because you will also include the external forces in this in here in this equation. Clear? So if you apply this external forces, the equation will be like this. And suppose this external forces, if you assume the gravitational forces, then equation will be like this. If resistance, you consider resistance, then this equation will be like this. These are different cases. Generally we are concerned with this equation. So this is the required wave equation. So I hope that you got the concept, and now you can derive the wave equation.